Radar is one of the most important technologies used in air traffic control. It is also one of the oldest. But what is radar? Where did it come from? What is it used for in the air traffic control system? My name is Kyle Warner. I'm an air traffic control student here at the University of North Dakota. We hope to answer these questions and more today on ATCast.
Thank you. JetBlue 1264, Boston, ground taxi ramp in November and Alpha. Boston Tower, Gulfstream 717, I perform 30 on the ILS 4 right approach. Hey, there's 741 is checking out. 741 Boston Tower, good evening. Thanks for calling 737 distance high melt. I'm like full right clear to land. Touch point 1015. 17, thanks for the service. Terminates clock VFR for continuing service. See you way back. Air 117, okay, good night now.
Radar stands for Radio Detection and Ranging. The technology dates back to 1904, when a primitive type of radar was developed in Germany for use on boats to prevent collisions in fog. The technology was refined over the years, and its military value was soon recognized. In the mid-1930s, the United Kingdom set up a network of radar stations along its coast, called Chain Home. This radar network was instrumental during the Battle of Britain early in World War II. It allowed for efficient use of the heavily outnumbered Royal Air Force, which could now be vectored to intercept specific threats. Instead of operating continuous fighter patrols, radar operators could provide fighter pilots with a target's location, altitude, speed, and direction of flight. Over the course of World War II, radar technology developed quite rapidly, eventually resulting in radar sets that were small enough to be carried aboard naval vessels and even aircraft. In addition to the development of radar technology, World War II resulted in huge leaps forward in aircraft design. They became faster, able to fly at higher altitudes, and able to carry more people and cargo. These factors and large numbers of trained pilots being discharged from the Navy and Army Air Corps led to a boom in commercial aviation in the United States. The dramatic increase in air traffic led to a number of mid-air collisions. The most notable of these collisions happened in 1956 between a TWA and a United Airlines aircraft over the Grand Canyon. Among the many reforms resulting from this incident was the widespread implementation of radar technology for air traffic control use. Most radar systems in use today are not fundamentally different from those that were in use by 1945. More recent technology, such as computers, has changed the way we process and display radar information, but the basic technology is the same now as it was in the late 1940s. Radar works by sending a radio signal from a rotating antenna. If that signal hits an object, a portion of the signal is reflected back to the antenna and appears as a blip on the radar display or scope. This is called primary radar, in that the only information provided about the target is its location relative to the radar antenna. On older scopes, the beam is sometimes depicted as a line that moves around the scope as the antenna rotates. Each time the beam hits a target, the target's position is updated on the scope. The complete revolution of the radar beam around the scope is called a sweep. On modern displays, such as stars, the sweep is not depicted at all, but as with older displays, the positions of targets are only updated when the radar sweep hits them. A complete radar sweep generally takes about 5 seconds in the terminal environment, so a target's position will be updated about every 5 seconds. In World War II, radar controllers had to calculate things such as target speeds manually, by using a grease pencil to mark the position of a target as it changed with each sweep of the radar, and then using a slide rule to calculate its speed. Today, air traffic control computers automatically calculate a target's ground speed and display it to controllers. This and other information displayed, along with the primary radar return, is called secondary radar. The advent of transponders and the Mode C function has allowed information such as altitude and SQUAWK codes to be transmitted back to the radar site and depicted on a controller's radar display as secondary radar information. In order to receive secondary information, an aircraft must be equipped with the proper type of transponder, and the radar site must be equipped with a beacon interrogator. As the radar signal hits the aircraft, the transponder detects the signal and sends back its altitude information and transponder code. Data, such as aircraft call signs, used to be written on a slip of paper and put on a shrimp boat, which was physically placed on the scope next to its corresponding blip, and pushed along as the target's position changed. Today, secondary information such as the aircraft call sign and type is entered along with other data when the aircraft's IFR flight plan is entered into the ATC system by flight service personnel and is depicted on the radar display as long as the aircraft is using its assigned SQUAWK code. Radar has two basic functions in the air traffic control world: airport surveillance radar, or ASR, and en route radar. Airport surveillance radar is used by both tower controllers and controllers in the Terminal Radar Approach Control, or TRACON. In the tower, ASR is used to locate aircraft within the tower's airspace. Some towers use the same type of radar display as the TRACON. Others use a type of scope called a BRITE, or a digital version of the same scope called a DBRITE. The TRACON uses airport surveillance radar to provide services and control instructions to aircraft in the arrival or departure phases of flight. TRACONs typically control the airspace within a 35 to 40 nautical mile radius of an airport. They vector arriving aircraft to the airport and issue approach clearances. Departing aircraft are vectored onto their initial courses and are issued climbs before being handed off to the en route center. The FAA is now transitioning TRACONs to the STAR system, which provides controllers with a number of enhancements, such as all digital displays. ARTS, or Automated Radar Terminal System, continues to be used in many TRACONs. Air Route Traffic Control Centers, or centers, use computer systems that track radar information from a number of different radar sites and combine that information onto a mosaic image that is displayed for the controller. This is how centers are able to cover hundreds of square miles with a single sector. Now for a brief review. Radar stands for Radio Detection and Ranging. It works by sending a radio signal from a rotating antenna. If a signal hits an object, a portion of the signal is returned to the antenna and displayed as a blip on the radar scope. Radar technology dates back to the early 1900s and hasn't changed much since the late 1940s. Primary radar is simply the blip that the sweep detects. Secondary radar is information displayed along with the blip. Air traffic control radar systems provide secondary information, such as aircraft call signs and altitudes, SQUAWK codes, and ground speeds. Altitude and SQUAWK code information is supplied by an aircraft's transponder, which sends the information back to the receiver at the radar site. Radar has two basic uses in air traffic control. These are airport surveillance radar, or ASR, and en route center radar. On behalf of UND Air Traffic Control, the Student Air Traffic Controllers Association, and the Aerospace Network, thanks for tuning in. My name is Kyle Warner, frequency change approved. For more information on UND Air Traffic Control and to see other videos in this series, visit www.aero.und.edu or search for ATCast on iTunes University.